Good morning.
Good morning.
Good morning.
All right, so let's see. Holbrook, Andres is there. No, he's not there. Is there anybody else absent in Holbrook? All right, Joseph City, we have Jill gone and Sari. All right, is that it? Everybody else? It's good. All right, so anybody have any big plans for the weekend? No? All right.
My family's going to Laughlin, Nevada.
Laughlin?
Yeah.
So is that for gambling your paycheck away, or what's the deal?
You know it. You know it.
All right.
And it's an hour away from Kingman, where my grandma lives, so we're going to visit her some too.
Okay. Well, listen, and when we get to chapter 11 in this book, I'm going to teach you there's a trick to winning craps 99.99% of the time. So I'm going to teach you how to do that. So
I'm going to have to pay close attention to that one, Jeff.
okay. All right. Well, there is one slight little hitch to it, but still it's pretty good. So, but yeah, that will give you something to look forward to in May, so anyway. Okay, well, you guys have a good time. Well, today we're going to finish up 6:4 and then start in on the last section in chapter 6, which is 6:5. So, anyway, so let's start here. All right, we've got. All right, let's see. Okay, so this is kind of where we ended up, practice 2A, and I'd asked you to determine the period of the sine and the cosecant functions and kind of, maybe look at their graphs and so on. And so if you look at the graphs here, here's the cosecant or the U shape, and then the sine is this, what I've got written here in blue. So what I'm hoping that you'll see visually, because I actually told you in the notes that sine and cosecant have a period of what?
2 pi.
2 pi. So I'm just wanting you to see it. So that, see, if we start here at 0 and end here at 2 pi, see, it makes one complete cycle. And the cosecant has one, like, U going up, a horseshoe going up, and one going down. So that's one period. Okay? So I'm just hoping from this example that you'll visually see that the period is 2 pi. So for sine and cosecant, cosine and secant, the period's 2 pi. Tangent and cotangent, the period's pi. Okay? So that's how long it takes to complete one cycle. All right, so now, the graphs of the tangent and cotangent. Now, basically, remember, tangent is sine over cosine. And so wherever the cosine is 0, you're going to have a vertical asymptote. So at negative pi halves, 3 pi halves, when you add pi to it, the cosine is going to be 0, so that causes a vertical asymptote. Okay? Now, when you put it in the calculator, again, you want to make sure you're in radian mode whenever you're graphing any of the trig functions. And it doesn't graph the vertical asymptotes. So you've got to know that, this is at negative pi halves and so on. Okay? Now, the tangent goes up from left to right from one vertical asymptote to the next. Okay? All right, so how would you put in cotangent? For the practice problem, I'm wanting you to graph cotangent. So how would you put that in your calculator? How do you put in cotangent to graph it? Because there's no cotangent key.
You have to do 1 divided by tangent of x.
Right. Okay, so again, make sure your calculator's in radian mode, and then do the y equals and 1 divided by tangent of x. And then draw a rough sketch of that on your paper for the next practice problem. Okay, so what you should see is the cotangent from left to right always goes down between the vertical asymptotes. Now again, the vertical asymptotes are not going to show up on your graph, and they occur every multiple of pi. So at negative pi, negative pi, 0, pi, 2 pi, every multiple of pi, you're going to have a vertical asymptote, and then you draw it going down from left to right. All right, so any questions on the graph of cotangent? Okay. All right, next. Okay, so because the tangent function is odd, the graph of the tangent function is symmetric with respect to the origin. Now, remember, for odd functions, that the way that you tell it graphically, see, if let's say if you have the tangent function put in your calculator like that, okay? Then if you actually turn your calculator upside down, you'll have the same graph. And so that's evidence of an odd function. It's symmetric through the origin. And so it's going to be the same if upside down. Now see, here's the cotangent. Cotangent is not exactly, oh, let's see, wait a second. Is it? Okay, so the cotangent is too. Okay, so let's actually go through the even and odd properties here. Okay, so the even and odd identities, all right? So the even identity, let's see, okay. So the even identities I've highlighted. So cosine and secant are even. And so notice with those, like the cosine of negative x, it's like the negative just disappears. So when it's even, it means it's symmetric through the y-axis. And so if negative xy is on the graph, so is xy. And so it's like the negative just disappears. Now with the odd identities, if you have a negative as part of the argument and part of the angle, then you can pull the negative out in front. And so all of the rest of them are odd. Okay, so the next part is going to be talking about how we transform the graphs. Just like you know how we did the shifts for the polynomial functions, like say the parent functions, and we would shift them up, down, left, and right. So we can do that with the trig functions, as well as change the period and what's called the amplitude or the height of the functions. Now, typically on these, I'm going to focus on sine and cosine. Okay? All right. So first of all, we're going to talk about the number a. If there's a number in front of the sine or cosine, that constant factor a in y equals a sine x acts as a height adjuster. So if the absolute value of a is greater than 1, the basic sine curve is a larger wave. So if you want to make the wave bigger, you change the number in front to be bigger. If the absolute value of a is less than 1, the basic sine curve is a smaller wave. So if you make it half or something like that. The result is that the graph of y equals a sine x ranges between negative a and positive a, instead of between negative 1 and 1. So the normal sine wave, the normal cosine wave, live between negative 1 and positive 1. So, but if we put a number in front, like say 5, then it goes up to positive 5 and down to negative 5. So it makes the wave bigger. So the absolute value of a is called the amplitude of the function. So y equals a sine x, the a is the amplitude. The absolute value of a is the amplitude. Okay? So, a lot of times when we're graphing functions to compare, we'll graph, let's say, like say y equals cosine x, and then compare these two. So here in gray, I have y equals cosine x. So then y equals 1/2 x would be this one. So instead of going up to 1 and down to negative 1, it only goes up to 1/2 and down to negative 1, down to negative 1/2. Or for the second one where there's a 3 in front, you draw the same cosine graph, but instead of starting at 1, you start at 3 and go down to negative 3 and then back up to 3. So it still has the period of 2 pi, but it's just a bigger wave. Okay? All right. So let's go see if you can do the practice problem there. Well, okay. So I remember somebody asked me, well, what does a negative do? If the amplitude is the absolute value, so here the amplitude would still be 2. But the difference is with when you have a negative in front, instead of like the sine wave going up to 2 and down to negative 2, it actually goes down first. So the negative reflects it through the x-axis, just like when we did before with polynomial functions. Okay? But the amplitude is always a positive number. Okay. So go ahead and try this one. Now, if you want it to be perfect, you can do it in your calculator. But really, if you just want to do a rough sketch on your paper, that's fine with me. Okay, so I just did a rough graph. So the original sign is here in black, and then the 2 sine x. So I had that go up to 2. It's a little bit sloppy, and then down to -2, and then back up. The 1/3 is in green, so it goes up to 1/3, and then comes down and goes down to -1/3, and then back up. Now they all start at the origin. Okay, so the sign goes through the origin. So if yours doesn't go through the origin, that's something that I would look for when I'm grading. I mean, if it's like this, where it's not perfectly symmetrical, or maybe it doesn't go all the way down to -1/3, okay, I'll probably cut you a little slack on that, but it has to go through the origin. Okay. All right, any questions on that? Anyone having any trouble putting it in the calculator? Okay. All right, next. We're talking about the period of these functions. It says, let b be a positive real number. The period of y equals a sine bx and y equals a cosine bx is 2 pi divided by b. So earlier I said that the period of sine and cosine was 2 pi. Well, so to change that, you put a number in front of the x. Okay? So the a affects the amplitude, the b affects the period. So it's 2 pi divided by b. If 0 is less than b is less than 1, so b is between 0 and 1, then the period is going to be greater than 2 pi. Because if you divide by a half, for example, 2 pi, like if b is a half, 2 pi divided by a half, well, that's the same thing as 2 pi times 2. So it would stretch it out. It would give you a bigger period. So that would represent a stretch of the graph y equals a sine bx. If b is greater than 1, then the period of y equals a sine bx is less than 2 pi and represents a shrink of the graph of y equals a sine bx. Okay? All right. So let's say I want to graph y equals the sine of x divided by 2. Well, the coefficient of x here is 1/2. So you think of b as 1/2. So in general, the formula is 2 pi divided by b. So if b is 1/2, you have 2 pi divided by a half, so that's 4 pi. So when you make your graph of the sine of x, see, instead of when it completes its period, normally it would be at 2 pi, but now it's at 4 pi. Okay? So when I'm doing it on my paper and I don't have coordinate axes to do it, okay, I actually cheat. Because what I do is I do the same graph. I just label the axes different. So I'll do the same graph for a sine of x as sine 1/2 x, only instead of labeling it from 0 to 2 pi, I just label it from 0 to 4 pi. Same graph. Okay? All right. But if you have axes and you have scales, then you got to deal with that. All right. So go ahead and see if you can do practice 3B. Okay, so here the main thing, couple of things. So when you're doing cosine, it does not go through the origin, it goes through 0, 1. So when you're checking your graph, make sure it goes through 0, 1. Okay, then when you draw one period, then this one also has a period of 4 pi. And so from here to here, one complete cycle, it should be 4 pi. And you should have that labeled on your x-axis. Okay? So two things I would want. Has the point 0, 1, and then when it goes through the period, you have 4 pi here labeled. Okay? Any questions about that?
It's not what he has up there.
Mr. Strong, I don't quite understand this. It's kind of confusing for me.
What is it that you're not understanding?
Oh, just kidding. He does have
Where'd
that.
you get the 1/2 from?
Okay, because that's the coefficient. The coefficient of x over 2 is 1/2. So x over 2, that's the same thing as 1/2 x. So that's the b for this problem. So then the period is 2 pi divided by b. So that's 2 pi divided by 1/2, or 4 pi. That make sense? Does that help? So let's say it was the cosine of 3x. Then the period would be 2 pi divided by 3. And so you would draw your cosine graph and then have it end at 2 pi divided by 3. So whatever the period is, you're calculating how long it takes to complete one cycle. Let's see if I've got... Okay. Let me just try something really quick here. All right, well, so if you're having some problems with that, one of the things that I would suggest you do is just kind of play around on the calculator a little bit so you can see some different problems. Okay, so let's see, I'm in degree radian mode. So let's say if I just graph y equals sine x. Let's see, okay, let's go back to the, oh. So I'm going to do zoom trig. Okay, so that's the sine. And so, so that is completing one period in 2 pi. All right, so now if I change the number in front of the x, let's say it's sine of 3x, or let's make it 2x. So that's shortening the period, because now the period is 2 pi divided by 2, which is 1 pi. So it's actually compressing the wave so that it's only half as long as it was before. So the period is getting shorter. All right, now in this example that we did before, if we do the sine of, let's say, 1/2 x, or x divided by 2. See, that's lengthening the wave. So now the period is 4 pi. So it's a longer wave, and so it's like stretches it out. Okay? So it's that number in front of the x that affects the period. And that's what we call the b. Okay, for these problems. All right, does that help? Any other questions on that? Okay. All right, so now let's talk about the c. So if we have a number inside the argument, so you have the bx minus c. The constant c in the general equations, y equals a sine bx minus c, and y equals a cosine bx plus c, that creates the horizontal or phase shift. So we did horizontal shifts with other functions when we did the graphs back in 152. And just like in those, the horizontal shifts move the opposite direction that you think. So if you have a plus in here, it's going to move to the left. If you have a minus, it moves to the right. Now, how much is the shift? Well, okay, so the period is still 2 pi divided by b, but the phase shift is in the amount of c divided by b. So I put a little star there because that's really what you really need to know the most from all of this, is that's how you get the phase shift, c divided by b. Okay? So here, if I'm given y equals sine of x minus pi. So here the c is pi. The b is 1. So the phase shift is pi divided by 1, or pi. And since it's a minus here, it's pi to the right. So how do you do that? Well, I have an advantage here on the smartboard, because what I can do is I can just do my regular graph of the sine, and then I just move it to the right pi units. So, I mean, you don't get to drop and drag unless you have a tablet or something you're taking notes on, but you just have to imagine. So here, instead of doing the regular sine graph, you're moving it over pi units. So instead of starting at the origin, it's going to start at pi 0, because you're shifting it to the right pi units. So c divided by b. All right, so go ahead and try practice 3c. Okay, so now on this one, we not only have a phase shift to deal with or horizontal shift, we also have to deal with the amplitude, and this one is 2. So hopefully you picked up on that as well. All right, so here, so if we start with just graphing the sine, so that's here in black. Well, no, it's not. If the dealing with the 2 sine x, that's what I have in black, where it goes up to 2 and down to -2. But see, this one has a phase shift of pi halves over 1, or just pi halves. And it's going to be to the right 5 halves, or pi halves, excuse me. So we take our graph, and then if we move it over here pi halves, then we're going to get the graph. And so I just had it start here at pi halves. It goes up to 2 and down to -2. And then I did a little bit more over in this direction here. Okay, so horizontal shift of pi halves, amplitude of 2. All right, so that's kind of what I'm looking for in that one. All right, any questions? Let's see. Okay, so for this one, it says to graph all of this. Okay, so here's what I want. Oops. Okay, so I want you to tell me what the amplitude is, what the maximum height is of the graph, what the minimum height is of the graph, what's the period, and what's the phase shift, and then try to graph it. All right, so Jay, what's the amplitude?
Half.
1/2, very good.
Half.
So it's the absolute value of -1/2, so 1/2. So the amplitude is never negative, okay? Right? All right, so Hannah, what's the highest the graph goes?
1/2.
1/2, okay? And what's the lowest the graph goes, Hannah?
-1/2.
-1/2, very good. All right, so Anna, what's the period? I got people flashing gang signs to me. So do you know, Anna?
I don't know.
Okay, anybody help her out?
I think it's 2.
It's
possibly.
2. Because remember, it's 2 pi divided by b. And in this case, the b is pi. So when you take 2 pi divided by pi, the pi's cancel, so you just get 2. All right, and then finally, the phase shift. All right, Madison, what's the phase shift?
One.
1. So it's c divided by b. So in this case, it's pi divided by pi, and it's to the left. So 1 unit to the left. Okay. Let's see, do I have the graph there? Yeah, so basically when you're graphing, I start with the sign, and then since it's so let's start with the sign. Okay, and then since it's negative, I'll flip it down. And then I'll have it only go from 1/2 to -1/2. So I'll label it like that. And then the period is 2. So I'll have it go from 0 to 2. And then I'll move it 1 unit to the left. So where this 2 is, I'm going to put that on the 1. And boom, there it is. Now, but on, go ahead.
How do you know which way it's gonna shift?
Okay, so it's going to shift c divided by b. So in this case, it's pi divided by pi. Now, if it's plus, it's like the horizontal shifts we did back with parabolas, is it goes in the opposite way that you think. So if it's a plus, you'll move to the left. If you have a minus in there, it moves to the right. Okay, awesome. Thank you for that question. Okay. All right, so then the last shift is the vertical shift. And just like with polynomials, the vertical shift is the easiest one of all. So that's the D. So when you have a D at the end, or I don't know why, some problems in your book, they put the D in front, and that's really annoying to me. But the D causes a vertical shift. If D is greater than 0, so if it's positive, the shift is up. If D is less than 0, if it's negative, the shift is down. And so then the graph oscillates about the line y equals D. So if it shifts up 2 units or something like that, instead of going up and down, oscillating about the x-axis, it'll oscillate around y equals 2. And so then you go up and down from that line. Okay? So it's just like having a plus 3 at the end of the polynomial, where it shifts the parabola up 3. The D shifts it up or down. Okay? All right, so here, the plus 2 at the end is going to shift the whole graph up 2. But, so we still do the other thing. So here, the amplitude is 3. The period is 2 pi divided by 2, which is pi. The vertical shift is 2. There's no horizontal shift, because if there's no C in there, there's no horizontal shift. Okay? Now, sometimes I also, again, ask for the maximum and the minimum. Now, this is a little tricky with the vertical shift. Not too tricky, really. But like here, the amplitude is 3. So normally, the highest point it would reach would be 3. But then you're shifting up 2 more. So the highest point would be 5. The lowest point normally would be -3. But then so from -3, you're shifting up 2. So the minimum point would be -1. Okay? Do y'all understand how I got those numbers? So you take the amplitude, The high and the low, and then shift up or down, as the case may be. Okay, so let's try.
Mr. Strong,
Go ahead.
sorry, I have a question.
Okay, please.
So what you're saying is that when you have the +2 there, you move the
Whole graph.
the whole graph. So does that mean that
Where's this?
that 2, that negative or that +2? Oh, now I see the whole graph. Okay, just kidding. I couldn't see the bottom part, so I was
Sorry.
confused.
As you started talking, I thought, oh, maybe I did a lousy job there. Okay, so go ahead and try practice 3E. And so I want you to answer the same questions, though. Is I want you to, let's write them up. Okay? So I want the amplitude, period, vertical shift, max, min. And in this one, there is no horizontal or phase shift because there's no C. There's no number in there. So I'll just even write that. Now, of course, if you're doing this as a quiz problem or a test, you can always check your work in the calculator. So that's kind of nice.
So I have a question.
Okay, please.
So it says 2x cosine x minus 5.
Yep.
I'm really confused. Is that minus 5 a C or is it a D?
Okay, that's a great question. If it were a C, it would have to be like that, because then it would be part of the argument of the cosine. Okay? So, but it's not. There's no parentheses there, so it's a D. So there is no C. That's why I said there's no horizontal shift. There's no C. So this is your A. And then, so if A is 2, what's B in this problem?
1.
1. And then what? And then we said there's no C, so C is 0. And then D would be
Negative 5.
negative 5.
The max.
All right, so Serena, what's the amplitude?
2. Oh, you marked.
2 is correct. Here, I think I've got it on the next page. Oops. Okay, so the amplitude is 2. Let's just write it down. All right. Lauren, what's the period?
2 pi.
2 pi. This is 2 pi divided by 1, so 2 pi. All right, Naomi, what's the vertical shift?
Wait, on practice 3E or which one?
Yep, practice 3E.
5.
Which way?
Down.
Down. So down 5. So minus 5 or down 5. Okay. All right. Desiree, what is the maximum? What's the highest point on this graph?
-3.
Excellent. And what's the minimum?
-7.
-7. Very good. Okay? So any questions on any of those? And so then to put it all together on the graph, see, because it's shifted down, it's down 5. So it's like y equals -5 is your axis of symmetry here. So then it goes up and down 2 from that. Okay. Any questions? Okay, so just briefly, this is a quick review of the graphs of the 6 trig functions. So sine and cosine look very similar. The main thing here is that the sine starts at the origin, cosine starts at 0, 1. All right? Cosecant and secant look very similar with the U shape. So the thing there is you've got to get the vertical asymptotes right. And so for cosecant, the vertical asymptotes occur where the sine is 0. And for the secant, the vertical asymptotes occur where the cosine is 0. Because it's 1 over that. Tangent and cotangent also look similar. Tangent is always increasing from left to right. Cotangent is decreasing from left to right. Again, you need to have the vertical asymptotes down right. So with tangent, the vertical asymptotes, it goes through the origin. The vertical asymptotes go through at -pi halves, 3 pi halves, and so on. Whereas for cotangent, the vertical asymptotes are multiples of pi. So 0 pi, 2 pi, 3 pi, and so on. Okay, so one last kind of bit of, sometimes they'll have a problem that will involve the frequency of a graph. Frequency is basically just the reciprocal of the period. They use omega for the frequency, and so if you just have, if you find the period and then take the reciprocal, that gets you your frequency. Okay, so if your period is 2, your frequency is 1 over 2, or 1/2. Okay, so now you might not know this, but radio waves look like sine waves or cosine waves. And so when you tune in a radio, I don't know if anybody does this anymore, maybe in your parents' car or something, as you turn in the radio, well, there's 2 different bands to tune in so that your radio is receiving the exact wave that the radio is broadcasting. So what are the 2 bands of radio waves?
AM and FM.
AM and FM. So anybody know what those stand for? Well, AM stands for amplitude modulation. So you're changing your receiver to match the amplitude or the height of the waves that the radio station is sending out. And so each radio station is going to send at a different amplitude. Okay? The other type, FM, is frequency modulation, which is, again, the reciprocal of the period. So it changes the period. Those change the period. The other ones change the amplitude. And so you can send out different types of waves. Okay? So just to kind of let you know. All right. Well, the last thing here on this sheet is what's called a damped signal. Okay, so let's see. Oops. I can. All right, come on. All right. So in the function f of x equals x sine x, the factor x, then the function in front is called the damping factor. Okay? What this does is it sort of gives you boundaries for your trig function. Okay? So let me just kind of show you what one looks like. So see how we have this function here? The damping factor in front, that's the damping factor, and that provides like the boundaries. So when you're trying to graph a function with the damping factor, you actually do plus or minus the damping factor. So for y1 is your original function, y2 here would be the function in front of the trig function, e to the negative x, and then negative e to the negative x. So those would be the damping functions. And so you put all those in the graph. Okay? So let's say for this one, what up there is the damping factor?
E.
E to the x. So this function in front. Okay? So if you were going to graph this with the damping factor, in your calculator for your y1, you just type in that. So what about for the y2? What would you type in? So for y2 and y3, it's plus or minus the damping factor. So you'll have e to the x and negative e to the x. Okay? So this is what you would type in. So the first would be the original function. Y2 is e to the x. Y3 equals negative e to the x. Okay? So I would like you to do that for class on Monday. And then if you have any questions, we'll go over it. But it just creates a boundary for your trig function. Okay? All right. Well, have a good weekend, and we'll see you on Monday.